Hello Year 11s, welcome to the second video of our chapter 16 and your holiday homework. So today we're going to focus on constant rate of changes. So last lesson you would have focused on what a rate of change looks like, okay, essentially a positive or negative gradient. So remember if we're walking up the hill or down the hill, okay. So a constant rate of change is when that rate of change does not change, okay, it's constant. AKA they're linear graphs, okay, and what does that look like? Okay, so first of all, our learning intention today is to recognize and calculate a constant rate of change within a graph. Our success criteria is I can calculate the values of both positive and negative constant rates of change within a graph. Okay, so what is a constant rate of change? As I touched on earlier, it's a linear graph. Okay, so a linear graph will have a constant rate of change, because if you think about it, the gradient at any point on that straight line does not change. Okay, so it's a constant rate of change. Okay, the three ways that we can recognize what a rate of change is. Okay, sometimes we're given the formula. Okay, so if we're given a formula of a linear graph, that's in the form of y equals mx plus c, as I've listed there. The gradient there is our m. Okay, so it's a value in front of that x. Another way that we can find it is our m, we could use our rise over run. Okay, so we could find the rise and run. We should be very familiar in how to find that. Or if we want to use the more algebraic, if we're given two coordinates, okay, we can go y2 minus y1 over x2 minus x1. Okay, listed like that. So those are the three ways that we can recognize a rate of change, a constant rate of change. Okay, use the one that you find will be best used for any particular question. Okay, so we have an example. A water tank contains 1,000 litres of water. That volume is decreasing steadily, and after 4 weeks there are 900 litres of water remaining in the tank. Show this information on the diagram and calculate the rate at which the volume is changing with respect to time. Okay, so one of the main things that we need to focus on is our variables of change. Okay, we're no longer talking x and y's. We've got it in the format of, if I change my pen color to blue, I've got my volume is now my y, and down here I've got my time, and that time is measured in weeks. Okay, let's see if I can write weeks. Now, what we need to do is represent this information. What does it look like? Okay, so at the start we had 1,000 litres, okay, and that coordinate right there I've listed there. So it's at 0 weeks, and we had 1,000 litres of water. However, what's changed? It's gone from 900 after 4 weeks. Okay, so what we've got is we've got a steady decrease within that graph. So let V be the volume after t weeks. So we have two coordinates, and those two coordinates are what we listed there. So the 0 and 1,000, and then the 4, 900. So to find the gradient, as I listed in the previous slide, that formula, we can find the gradient as y2 minus y1 divided by x2 minus x1. That gradient is 900 minus 1,000. Okay, so I've listed this second graph. If I could find my cursor, this second graph is my x2, y2. Okay, and that first one is my x1, y1. I'll put a little comma in there. Looks like an 11. There we go. As my first coordinate. So what I put there is negative 25, because we know that we're walking down the hill as we got that slope, so we're expecting a negative answer, and that answer lets us know. Just a reminder, it does not matter which way you put those y2 and x1, y1 or x2, y2 into that formula, as long as you're consistent. I always find it's easy labeling at the start. Okay, so as we go to our next example, we've got 3 cars driven down a 2-kilometre straight line. Okay, each car travels with a constant speed. It is not a race, as the speed of speed of car Y is twice that of X, and the speed of car Z is twice that of car X. Okay, illustrate this situation with a distance time graph. So what I've done on the left-hand side is I've set up our distance time graph. Okay, so the distance is my Y variable. Okay, so I could list my Y up there, and my time is my X. Okay, what you'll find is time is pretty much always your X. Time is never really a response, as we call it, so it's never really a Y variable. It's always an abbreviation for X that we can use. Okay, so I've listed that to from time 1 to 4 minutes, and on the y-axis we've got a distance of 2,000 and 1,000 meters. So what we do is car X. Okay, so car X travels at 1 kilometre per minute. So for it to travel 2,000 metres, as I draw a dotted line across, okay, it takes 2 minutes. So I can draw a dotted line going down like that. Okay, so if it's 1 kilometre a minute, 2 kilometres, 2 minutes, or 2,000 metres. Now, what we need to do is focus on the speed of car Y. Okay, speed of car Y is twice that of car X. So there's not, if we're travelling twice as quick, that does not mean we're travelling time after 4 minutes. That means we're travelling 2 kilometres in half that time, okay, because we're travelling twice as fast. So what we have is car Y has actually travelled 2,000 metres in 1 minute because the gradient has increased. So what you'll notice is with my car X, my gradient there, my M, is 1, okay, because as we fall over here, my gradient is 1 kilometre per minute. If we're travelling twice as fast, we know twice is a multiplication of 2, okay. So my gradient of car Y is actually 2. Now, if we're focusing on car Z, if it's half that of car X, that means if it's half, that means we're dividing by 2, okay? So what you'll find is our car Z, the one in the yellow, our gradient for this instance is 1/2. Okay, so we get the half that's there. So we have our 3 that are there. So if you illustrate the situation, so what we've got is a few little notes. So the gradient of car X is 1 kilometre per minute, okay? That's what we found. We're pretty happy with that. The gradient of car Y is 2 kilometres per minute. As we said, the gradient is 2, so that's its rate of change. Okay, remember, our rate of change, we're looking at it. We're travelling a distance over a certain amount of time. It's not just distance or just time. We're combining those two variables together of kilometres per minute, and that is our rate of change. Okay, and our gradient for car Z is 2,000 metres. However, it's taken him 4 minutes to travel that time. So he's actually travelling at 1/2 kilometre per minute. Okay, so what we've got is we've got a few questions. So those are the questions for you for 16B. So 1, 2, 3, 4, 5, 7, and 8. Please make sure you get a few of these notes in your band reference. Complete those questions, and once you've completed those questions, then we can move on to exercise 16C. Okay, thank you for listening.